Okay. Good morning. Thank you for coming in. I thought I'm going to be lonely, but you guys are still around. Okay. So what I've shown you over the past 3 lectures is okay not to understand what is going on. It is a preview to a horror movie. Okay? It's a preview to a horror movie. And on week 7, this horror movie will turn out to be an acceptable movie for you. Are we clear? Okay. I decide to do that because in the past, when I don't do that, students always thought, this is 2P. This is 2P will be fine. So you realize that I hope I drive the point that this is not the same. Yes or no? If not, I'll do another 3 hours of introduction. No. Thank you. Okay. I hope the lights are acceptable. Let me see. Will this help? Come on, come on, come on, come on, come on. Okay, this is enough. Okay, right. So today, we are going into the agenda for today. So this is 3A. And it's on a Friday. And our agenda for today is we are going to look at centric, symmetrical, pure bending. So I believe Dr. Koshi have touched this with you all, but I'm still going to go through introduction because some of you have done this at least 18 months ago. Okay. So let me ask those of you who have done the course last term. What do we mean by symmetrical? Anyone? Why we call it symmetrical bending? And then later on, there is unsymmetrical bending. What is this symmetrical bending? What does this actually mean? I see no takers. Yes. No, in terms of pure bending, no. Yes. The force go to the centroid, there's no torque. Nearly there. Yes. Symmetrical cross section. Next one. Anyone? Good answers. I need to talk to Dr. Koshi. Okay, good answers. Okay. So I did not know why also when I was your age. Okay, why symmetrical? And I start making guesses. Geometry, forces, okay, cross-sectional area, okay. So I'll go through explaining what is symmetrical pure bending first, okay. So now, if we have a structure, this is X, this is Y. I need your help from now on. I realize that sometimes when I write, I get excited. It's not readable. Okay. Can someone like be brave? Not be brave now. Tell me, Eugene, calm down. Write properly. Can we do that? Okay. Because when I look at my notes, it look like shit. I feel really pissed off. Okay. So this is our rotation about Z. I'm going to show you 2 types of loading. point A, point B, EY. Okay. And the distance from here to here is L over 2. Distance from here to here is L over 2. So this is our structure number 1. And then we look at another structure, which I'm going to draw by the side. This is a pin. This is a roller. By the way, you have seen, before I go on, you have seen, we call this a pin, right? We call this a roller. So what it means is the boundary condition states that x is equal to 0, y is equal to 0. On the right-hand side, y is equal to 0. X is not necessarily equal to what? 0. Okay? How does it look like in the real world? Yes. And then on the other side? So how does it look like in real life? You are right. I'm not saying that you are wrong. Have you been under a bridge? Or those of you who drives or walk to any bridge, okay, go below the bridge and have a look. And what you will see is this. The left-hand side of the bridge, this is concrete, okay? And this is where they place the bridge. On the other side, is it the same? It's not the same. You only have concrete down here, and the rest is free to move. That's what it means. I know it sounds crazy, but I think all of you should just go under the bridge and see this for yourself. What we write down here, draw down here, yeah, okay, but actually, how does it look? Because it's important. Until you see what it actually look like, then you can design. Are we clear? Okay, or not like, and then with this context, you can see any structures, okay? You can look at it, then you understand the restriction, or not like, yeah, whatever. Am I right? Okay, coming back to here. The second structure on the right now, okay, we have P, Y, okay? So the distance over here, from here to here, is L over 3. And here to here is L over 3. The distance from here to here, L over 3. Okay. Structure condition on the left, condition on the right. Which one is symmetrical bending? Anyone? Yes. On the left. Hey, don't feel shy. It's okay. Because when I was your age, I will also say on the left. We make mistake here, and that's it. When you go out, you do the same, I'll come after you. Okay? So one say on the left, Any others? Yes. Both of them are symmetrical bending, or none of them are symmetrical bending. None. You're killing me, man. You're killing me, man. Okay. You can't tell. You can't tell from here whether is it symmetrical or unsymmetrical. Sorry, you can tell. Sorry. Rewind. Both of them are symmetrical bending. Symmetrical bending has nothing to do on the location where the force of the distributed load is acting on, or whether the one on the left, where you see the load is in the center, the left and the right have equal distance, has nothing to do with it. Whether it's symmetrical or unsymmetrical is dependent on stress distribution. Okay, so whether it is symmetrical or non-symmetrical is dependent on the stress field distribution. So some of you might say, what do you mean by that? Okay, so I'm next going to draw 3 or 4 different cross section. Okay, and what I'm going to do now, we are going to draw the cross section. Okay, so by following the transformation now, right, this will be my y, this will be my z, this will be my x. So where are we viewing from relative to the structure over here? On the left, we are viewing here. Okay, these are my eyelashes. This is my eye. I'm looking from the left. Okay, so I'm going to draw 3 different cross-sectional of 4. Okay, so the first one, it looks like this. Okay, I'm going to call it alpha, beta, I, and j. And then the next one, we are going to have a T-beam. Alpha, beta, I, and j. And the third one, alpha, beta, I, and j. Okay. Do I need another one? No, I think this is enough to drive the point. Okay. So I'm now going to draw the centroid. Can anyone tell me the difference between centroid and neutral axis? Don't you dare come up with me and tell me it's spelling. Anyone? Yes. So this is the centroid. Okay. So over here, this is the centroid. To find the centroid, is geometry based. I repeat again, to find the centroid is geometry based. How about neutral axis? What happens at the neutral axis? Yes. The forces or the stresses. So centroid is dependent or position of the centroid is dependent on the geometry of the structure. Come on, Eugene, cool down. Okay. So position of the centroid is dependent on the geometry of the structure. So when I draw that as a centroid, the top half and the bottom half have about the same what? Not have about exactly have the same cross-sectional area. Yes? And then for number 2, this is just guess 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5. I don't know where it is, but I'm just making a guess. Okay. This is my centroid. Okay, for this case, we are very sure that this will be our centroid. Okay. Now, question for you all. Then what is a neutral axis? Yes. So you're partly right. Usually, when we consider, this is in structure analysis, okay?